Hello, and welcome to your first lecture on generative models. So before we get into the technical details of generative models, I wanted to give you some examples of what people have done recently with generative models. One of the most common things you'll see people talk about in blog posts or tutorials is using generative models to generate new images, like, for instance, new faces. On the left, you can see a model that has been trained to generate new anime faces. And on the right-hand side, you can see a model that generates human faces. And there are many types of models that do this, including one like this that creates human faces, although they're a little blurry around the edges. And we don't just have to generate faces. You're probably familiar with reading news stories or tweets about models like this that can actually take in a prompt and generate images for you according to that prompt. We can also use generative models to do in-painting, where we basically occlude part of an image and ask the model to fill in what it thinks should go in that missing piece. While it's not perfect, you can see even models like this are pretty good at figuring out what went behind the occluded region. And of course, we are all familiar with generative models like GPT that generate text in response to a prompt. Very recently, someone set up a generative model to write an infinitely looping Seinfeld episode and then use generative art to basically illustrate it. And as students who are taking tech-heavy courses, you're probably familiar with GitHub's Copilot, which is a generative model that creates code. For the more artsy among you, generative music models are also huge right now. For instance, there's a model called MuseGAN that generates new music, as well as a project from Google called Magenta that does generative music AI. Even the video game industry can use generative models, for instance, for level design to dynamically create new levels. And we don't just have to create completely new images. Style transfer is a huge part of generative models as well, where we take the style of one image and map it onto another. On the left, you can see this type of model with faces. Here, we're taking the style from the image on the y-axis, and we're mapping it onto the pictures on the x-axis to create a combination where the image has the style of the style photo, but the actual content of the actual content photo. You can also create some really cool things with this. For instance, I'm a big Breath of the Wild fan, and this is a picture from Breath of the Wild that has been used with a style transfer model to basically recreate the image in the style of Starry Night. We can also use generative models to modify images. For instance, this is a generative model that actually ages or de-ages of photos. You can see what you looked like maybe as a teen and as a 60-year-old. We can also use generative models to upscale images, basically take a blurry image and upsample all of the pixels to create a more sharp image. You know in movies when they always say enhance and they take a blurry photo and they zoom in and suddenly it's like this perfectly full resolution photo? Well, that's basically what this can do. Another example of this was something that my husband, who's a video editor, actually used. This allows you to take video that maybe looks a little bit blurry and upscale it so that it looks like a sharp image. And of course, you've probably seen generative modeling in your day-to-day media. For instance, Star Wars has been using a lot of deep fakes in order to de-age or even map one actor's face onto another actor. For instance, when they did Luke Skywalker in the Book of Boba Fett or The Mandalorian. And even if you're not familiar with that example, I'm sure you're familiar with Tik Tok filters. Traditionally, Tik Tok filters use something called face mesh. This is basically a model that uses AI to map a bunch of different points, usually a couple of hundred, onto your face. So it sort of learns where different things on your face are. And then it uses that mesh in order to place things on your face, things like makeup or a bunny rabbit or blush or something like that. And while these look pretty cool and are really fun, like Snapchat filters, they do tend to lack a sense of realism. You can tell they're clearly a filter. And not just because there's a bunny on top of your head, but because when you move around, sometimes it takes the filter a little while to catch up, or if you move your hand in front of your face, it maybe maps some eye makeup or blush or lipstick onto your hand rather than your face, because it gets confused about where your face actually is. But applications like TikTok have also been experimenting with generative filters. For instance, if you've ever used the bold glamour filter on TikTok, you might notice that it looks a lot more realistic and moves a lot better than these traditional face mesh filters. That's because these filters are using generative AI in order to recreate every single pixel of your video, rather than just mapping something like makeup or an animal on top of your video. This allows you to move around or wave your hand in front of your face, move your skin around, and the filter still works because it's learned how to take your raw video and map it to a version that has whatever effect the filter wants to use. And while we've talked a lot about very cool uses of this generative AI, there's also some nefarious uses. For instance, scam callers are now more and more using generative AI to clone people's voices so that if they get a sample of you speaking, they can then make a model that will generate you saying whatever it is they want you to say. For instance, calling up your grandparents and telling them you need $10,000 in order to get out of jail. And this isn't the only concerning use of generative AI. For instance, we can create videos or images of people saying or doing things that they didn't actually say or do. And at this point, it can sort of be hard to tell what's real and what's fake. So we've seen that generative AI is incredibly popular and it's definitely integrated itself into our daily lives. So let's learn a little bit about how this generative AI actually works. So there's basically two main types of generative models. The first type of model is a density estimation model. The goal of these types of models is to take in some data and learn a probability distribution that describes that data. For instance, we could fit a normal distribution to a sample of data. Once we know what that actual distribution is, we can then pull new samples from that distribution, thus generating new outputs. The other main type of generative models are sample generation models. These models have a similar goal. We're going to take a bunch of different inputs and we are going to somehow learn to just create new outputs. And we don't necessarily have to create a probability density function in order to do this. And with all of the examples we talked about, you might be thinking, wow, generative models are so cool and so complicated, but it turns out you've already learned some generative models in CPSC 392. Those models are naive Bayes and Gaussian mixture models. Let's look at a really cool example of using naive Bayes as a generative model. This comes from the book Generative Deep Learning by David Foster. In this example, we're going to look at a bunch of different faces. And these faces have a bunch of different features. You can wear glasses or sunglasses or no glasses. You can have different hairstyles, different colors, and different shirt styles. And we can use naive Bayes as a generative model here to create new faces. In order to do that, we have to learn a distribution of our data. In this case, we're going to learn a discrete distribution that looks at things like the probability of having glasses versus the probability of having sunglasses versus the probability of having no glasses. For instance, here, 22 out of 50 faces have glasses, so the probability of glasses is 0.44. The probability of having sunglasses is 17 over 50, or 0.34. And the probability of having no glasses is 11 out of 50, or 0.22. And we could do this again for each of the different features like hairstyle, hair color, and shirt color. And now that we have these probabilities, we can use them to generate new samples. And we're going to do so by making the naive assumption in naive Bayes, which is that all of our different features like glasses, hair, shirt are all independent. Because of this independence, we can actually generate new samples that have never been seen before in our original training data. For instance, in order to figure out if a new sample is going to wear glasses, all we have to do is sample from this probability distribution, which tells us that 44% of people wear glasses, 34% wear sunglasses, and 22% wear none. Using all those probabilities, we can then generate new samples like these. Thus, we've turned our naive Bayes model into a generative model. But this data is pretty special. It's labeled data. Someone has gone through and recorded whether or not people are wearing glasses or sunglasses and what type of shirt they're wearing. And this is often not the type of data that we will have in real life. So let's look at a similar example where instead of having labeled data of different features of faces, we actually just feed the model the picture of the face itself. Here you can see pixelated versions of these faces. And like before, we're going to use a naive Bayes model in order to generate new images. But instead of feeding it individual features, we're going to just give it all of the different pixel values. It can then learn what the probabilities of each pixel being a different color are and sample new pixels to generate new faces. If we did that, it might look something like this, which doesn't actually look that great. This is because our model is not taking into account the fact that nearby pixels are probably going to be similar colors and represent similar features. And this is something we might want our generative models to be able to do. Next, let's talk about Gaussian mixture models and how those could be generative models. Remember, in Gaussian mixture models, which we've previously learned mainly for clustering, we assume that the data that we observe in a population is made up of different mixtures of two or more groups of different populations. For instance, here we have some data on how much money people spend on fast food per week. We have one distribution which seems to be pretty heavy fast food buyers, and another distribution that seems to buy a little bit less food on average, but is still occasionally spending a little bit of money. We're assuming that the data we observe, this purple line, is a combination of these two groups of people, our heavy spenders and our not so heavy spenders. And back in data science, this is pretty much where we stopped. We wanted to figure out which data points were in each distribution. But notice we are explicitly modeling a probability distribution that describes the data we have. So once we do that, we can just sample from it. For instance, now that we learn these two distributions, the red distribution and the blue distribution, we can just sample new points from them. For instance, I might take this sample from the red distribution, and then this one, and then this one, and then this one from the blue distribution, and this one from a blue distribution. And because we explicitly modeled, in this case, normal distributions on our data, we can actually generate new data that we haven't observed in our original data set before, thus generating new data. In 2 dimensions, it might look something like this. Here's our original samples of groups of data, and these red points represent the new generated values that we see. Well, they're very similar to the data we learned because, of course, we want realistic samples. Not all of these are actual points that we've observed before. Thus, we're generating entirely new samples based on the distributions that we learned. So it turns out you already knew how to do generative modeling. Both Gaussian mixture models and naive Bayes do explicit density estimation by learning probability distributions that describe our data. In Gaussian mixture models, we assume normal distributions, whereas in naive Bayes, we are typically looking at probability distributions that describe the different probability of discrete variables like glasses, sunglasses, or no glasses. However, these two models are pretty simple, and therefore they're limited in the types of generation that they can do. So let's talk about another generative model that explicitly does density estimation, the variational autoencoder. Autoencoders should be a bit of a review. In the previous lecture on autoencoders, we talked about them as compression. We feed in an input, the autoencoder then creates a hidden representation that then can be used to recreate that input. The job of an encoder is to learn a function that takes our raw input and maps it to that hidden representation. The job of the decoder is to take that hidden representation and regenerate the input. Autoencoders, when we were using them for compression, what we were really after was this hidden representation because it represented our original data in a hopefully lower dimensional way. The success of an autoencoder was measured by its reconstruction loss, how well the output spit out by the model matched the input. A perfect model would be able to perfectly recreate the output based on the input. When learning about autoencoders, we also talked about how sometimes autoencoders are overcomplete, meaning that their hidden representation isn't necessarily a lower dimensional representation compared to the input and output. However, in order to avoid overfitting and still hopefully do some useful representation, we talked about different ways that we could modify our model so that it would still learn a useful representation despite the fact that the hidden representation was higher dimensional than the input and the output. One of the ways that we did that was by penalizing derivatives of our encoder. By penalizing the derivative of our decoder, we basically asked our model to make sure that inputs that were similar would also have similar hidden representations. When the derivative of the encoder with respect to the input is high, it means that a slight change in the input would lead to a large change in the hidden representation. And we wanted to punish that to make sure that our model represented similar inputs with similar hidden representations. All right, now that we've reviewed autoencoders, let's talk a little bit about variational autoencoders, which use a similar autoencoder structure to build a generative model. One thing that's really nice about well-built autoencoders is that they have things called concept vectors. Concept vectors are things like a smile vector, where as we move along the vector, we can get more and more of a smile, like in this pretty creepy image. Similarly, if we move backward along the vector, we get less and less of a smile. This is really similar to a concept we talked about when talking about language models. For instance, when we had word embeddings, we had vectors that represented context. For instance, we looked at a vector like this that represented the idea of a king minus the idea of being a man. Put together, this is the vector that represents the concept of being royal. Thus, as we move along the direction of that vector, we get more and more royal, going from man, who's not very royal at all, to king, who's pretty darn royal. So how do we build one of these variational autoencoders? Typically in an autoencoder, we input something, whether it's a vector of numbers or an image, and we grab a hidden representation where we take that image and represent it with a vector of numbers. We then take that vector of numbers and ask the decoder to recreate our original input, whether it's an image or just a bunch of data. Variational autoencoders do something very similar, except instead of just a vector of numbers as the hidden representation, we actually use a probabilistic hidden representation. This means when we have an input, our encoder actually learns a distribution of likely features. For instance, in this photo, we might have this distribution for a smile and this distribution for glasses. So instead of single numbers, we actually have our data being represented by a bunch of different distributions. The idea behind variational autoencoders is that if we learn distributions for each of these features, we should be able to sample slightly different values from that distribution to generate a new random hidden representation. And any sample from these distributions should create a very similar image to our input. For example, here you see these same distributions that we saw on the previous screen, where from the input image, we learned that there's probably a very slight smile and the gender is probably slightly more masculine. We then sample different values from each of these distributions, and the red dots represent the samples for this, and the yellow dots represent the samples for this. Both of these are turned into vectors of hidden representations, and both are sent through the decoder. The decoder then takes all of these values and recreates an image. Because an autoencoder is still judged on whether or not it can recreate the original image, we expect that both of these very slightly different samples are going to generate incredibly similar images, both that are similar to the original input face. This is similar to penalizing the derivative of a typical autoencoder. When we're penalizing the derivative of a typical autoencoder, we're telling our model that slight differences in the input should not lead to huge differences in our representation. A variational autoencoder, on the other hand, says that slight differences in our hidden representation should still produce very similar output. So variational autoencoders are very similar to our typical autoencoders. In regular autoencoders, we represent our data using a latent or hidden representation. This representation is usually just a collection of numbers that are then used by the decoder to recreate our input. Variational autoencoders, on the other hand, don't have just stable numbers as their hidden representations. Rather, we learn distributions of values to represent our hidden representations. representation. Thus, variational autoencoders are more probabilistic in their hidden representation. The job of the encoder is to learn what is the hidden representation given my input. And the job of the decoder is to say, what do we think my input was based on the hidden representation? To review what this process looks like, we are going to take an input like an image and send it through our encoder. After training, our encoder is going to learn a probability distribution across the hidden representation. So instead of learning a single value, it'll learn a distribution of values that are all nearby to each other. Then we can take various samples from this learned distribution and send them through the decoder. No matter what sample we have, we expect that our decoder is going to generate something very similar to the input to our model. Thus, the model has to learn that data points that are near each other in the hidden representation need to create similar output. So let's look a little bit more about how this structure actually works. Remember, in a typical autoencoder, we have an input. We send that through an encoder, which could be multiple layers of dense or convolutional neural net layers. We then come to a learned hidden representation. We feed this representation to the decoder, which hopefully spits out an output that looks a lot like our input. In a variational autoencoder, we add a couple of new steps. We still have an input. This is going to be an image or some data that we're feeding into our model. We then send it through an encoder, but instead of just learning an individual vector of numbers, our encoder is going to learn a distribution. In variational autoencoders, this is typically a multivariate normal distribution, which has a couple of parameters, including the mean of the distribution, mu, as well as the standard deviation of the distribution, sigma squared, as well as the variance of the distribution, sigma squared. So instead of learning one individual vector of numbers for the hidden representation, our encoder actually learns two. And just like with our typical autoencoders, this encoder could actually be multiple different layers of convolutions, dense layers, etc. In variational autoencoders, we are not going to learn a single vector of numbers as our representation, but rather a vector of means and variances that describe the multivariate normal distribution that is our hidden representation. We then need to sample from that distribution, and one way to do that is to just generate some random noise to add to our mean and our variance. This noise is completely random and not something that is actually learned by the model. When we combine these three things by taking the mean, adding the standard deviation multiplied by the noise, we basically get a random sample from our hidden representation distribution. Again, the mean describes where the center of our distribution is, the variance describes how wide and spread out the distribution is, and the noise basically generates some randomness to sample a random value from that distribution. This is our final hidden representation. Like in a typical autoencoder, it is fed into a decoder to then hopefully reproduce the input as our output. And just like in an autoencoder, this decoder could be multiple stacks of different layers. Just like an autoencoder, the goal of a variational autoencoder when training is to recreate our output based on our input by first encoding and then decoding our input. In a variational autoencoder, the encoder first learns a mean and variance for our multivariate normal distribution, then samples from that using this noise value, and adds them all together to create our final sample from our hidden representation. This is then fed into the decoder. The decoder's job is to take this sample of our hidden representation and process it in order to create our output. And the goal of our output is to be as similar as possible to our input. If your brain works a little bit better in code than in pictures, here's some pseudocode for how a variational autoencoder works. First, our encoder is going to learn the mean and the log variance of our multivariate normal distribution. The reasons for learning the log variance compared to the actual variance are more mathematical than conceptual, so we'll skip over them here. Once we've learned the mean and variance of the hidden representation, we can then sample from it by using this formula that combines the mean, the variance, and a random value in order to generate a sample from our distribution. For instance, if you see this image on the right that shows a multivariate normal distribution, we could grab a sample like this from that distribution. Now that we have our sample, we can send it through the decoder, which is a function that is trying to learn how to recreate our input based on this sample from the hidden representation. Because we're taking random samples from a distribution, we expect that similar but slightly different hidden representations are going to generate very similar images. Because remember, the goal of our variational autoencoder is still to recreate our original input, but we expect different random samples from the learned distribution to generate that same input. So, hidden representations near each other should generate similar output. Now that we've talked about the structure of a variational autoencoder, let's talk a little bit about how it's trained. When we learned about autoencoders, we learned that they use something called reconstruction loss in order to train. Reconstruction loss basically just compares the inputs to the outputs element-wise and sees how similar they are. A perfect autoencoder would have a very low reconstruction loss because the inputs would be very, very similar to the output. And variational autoencoders are no different. We're still going to consider this reconstruction loss because we still care that our inputs and outputs are similar to each other. But we add another penalty or regularization term to this loss function. We're going to use the KL divergence of the representation we've learned, that multivariate normal distribution, compared to a standard normal distribution. Remember that the variational autoencoder is going to learn a mean and a variance for our multivariate normal. We're going to compare that to a standard normal that has mean of 0 and variance of 1. Remember, the KL divergence is a way to measure how much information is lost when we represent one distribution as another. For instance, in our math review lecture, we talked a little bit about how much information we would lose if we represented this distribution of car colors using a uniform distribution. KL divergence is basically a measure of how similar two distributions are. If we lose basically no information by representing one distribution as another, then basically these two distributions are practically the same. Thus, this KL divergence term encourages the normal distributions that we learn to be similar to a standard normal distribution. And why would we want to do that? Well, it makes the hidden representation of our data have really attractive features. Here on the screen, you can see some examples of what happens when we train a variational autoencoder with only the reconstruction loss in mind. So all we care about is that the inputs and the outputs are similar. Here, the data is representing individual images, and you can see that different numbers are kind of close to each other. There's little regions of like 1s versus 2s versus 0s versus 6s. In the middle, we have an example of an autoencoder trained only on the KL divergence. While this has a very symmetric and beautiful normal distribution of points, we didn't really learn anything about our input. Basically, inputs that are similar are not necessarily close together in their hidden representation. And neither of these are exactly what we want, which is why we combine them. We consider both the reconstruction loss as well as the KL divergence. When we combine them, we get this really nicely behaved latent space where items that are similar tend to be very close together in their hidden representation, but we have these nicer looking distributions compared to when we trained only on reconstruction loss. When we train an autoencoder, there's nothing telling the autoencoder that similar inputs should have similar hidden representations. For instance, here in this example, you can see that our square and our rounded triangle have very similar hidden representations, despite being very different shapes. Ideally, what we would like is for similar inputs to have similar hidden representations. For instance, like this, where the triangle and the rounded triangle have very similar hidden representations. Another thing we might want from this latent space, our hidden representation, is for us to have a continuous space that represents real shapes. For instance, here we've learned representations of our different shapes where circles are near circles in the hidden representation. But if we sampled a random spot between them, we would get something that is not actually a shape. And we might want to learn a space where all the points in that space are actual shapes. For instance, in this one, we have our triangles, our circles, and our squares. But if we sample something between all of those, we get basically a valid shape that is a combination of a triangle, a circle, and a square. And if I sampled another point here, I might get something that's a mesh between a circle and a triangle, or here between a square and a triangle. And this property of the latent space is really useful. For example, here's a visualization of the latent space for a variational autoencoder trained on the MNIST dataset. You can see that as we sample from different points in the space, we seamlessly move between digits. For example, here you can see we move from a 0 and we get closer and closer and closer to something that looks like a 6 and then a 5 and then maybe like a 9 or an 8. And you can see with this continuous latent space that we're able to basically morph between objects. For instance, here we have something that is very clearly a 9. And as we move in any direction, you can see it slowly morph into something else. Like, for instance, in this direction, we're morphing from an 8 to a 3 to a 2. And as we move through this space, we basically move from more and more like a 9 to more and more like an 8 to more and more like a 3 in a continuous way. And I don't know why you'd want to do this with digits, but this is useful because then we can ask, okay, I want something that's, halfway between an 8 and a 3, and we can actually just sample something like that that's between an 8 and a 3. So variational autoencoders basically learn a hidden representation or a latent space that has some really desirable properties. The main characteristics of these properties are representation, realism, and smoothness. An ideal latent space will have good representation. That means that we can take an input, encode it, and then decode it and accurately reconstruct our original input. This is something that it shares with traditional autoencoders. But the ideal latent space of a variational autoencoder will also have realism. Realism means that we can sample any point in our latent space, and we should get something that looks like a valid input. For instance, here in this variational autoencoder trained on shapes, we should be able to sample from any point and get something that looks like a valid shape. Finally, an ideal latent space for a variational autoencoder will have good smoothness. Smoothness means that in our latent space, we can basically pick two different points and gradually move between them, morphing from the first point to the second. For instance, in this example, from a variational autoencoder trained on human drawings, we can take this drawing of a cat's face and this drawing of a pig's body and slowly morph between them, creating things that look like valid drawings at every step. For instance, here we start with the cat, and then we move over as we move through the latent space to things that are more and more pig-like compared to the original cat face. And as we move all the way here, we finally get something that looks pretty like our original pig. This smoothness means that we can sample this latent space all the way from cat face to pig body and get accurate representations that move from very cat face-like all the way to very pig body-like. All right, before we move on, I just want to make one quick technical note. We've been talking a lot about variational autoencoders that process images, and as you can imagine, the encoder and decoder both have convolutional layers in them. However, there's some differences compared to how we build typical convolutional nets for classification and how we build our convolutional encoders and decoders in a variational autoencoder. First, convolutional neural networks for learning features preferred max pooling to strides in order to downsample our image. That's because in the convolutional networks that we were learning before, we really cared about learning features, like, is there a wheel in this image? Is there a face in this image? We really cared more about whether something was present compared to where something is in the image. Thus, we had a really strong preference for max pooling, which allows you to do that. It asks basically, is there a heart in this image, rather than where is the heart in this image. However, max pooling does not preserve the location information of a feature. We basically just know there is a heart here, not where that heart is. But in variational autoencoders, it's often really important to preserve that location information because our goal is to recreate the original image just as it was, not just that there's a heart somewhere in it. So in convolutional variational autoencoders, we often use strides rather than max pooling in order to downsample our images. That way it'll preserve information location. Thus, when we use convolutional variational autoencoders, we often use strides rather than max pooling in order to downsample because it preserves the information about the location of objects in an image. As a general rule, you should use max pooling when you care more about what is in an image, and you should use strides for downsampling when you care more about where things are in that particular image. Last but not least, I want to share with you this really cool musical variational autoencoder, which is demonstrating the smoothness of the latent space in a variational autoencoder. The smoothness that we talked about the latent space, where we can go from one sample to another with all of the continuous values in between that look like real samples but slowly move from our first sample to our second sample, is often referred to as interpolation, where we go from one sample to another, slowly morphing between them. This musical variational autoencoder from Magenta does exactly that. It morphs between two samples of music, giving you samples in between that slowly move from the first sample to the second one.